Hello, my name is Muzammil. You can call me Muz, and welcome to my channel. In this video, we're going to be taking a look at how to calculate the volume of a solid of revolution using the disk method. But before we get into that, just keep in mind this video is going to be brief, and we will only cover the disk method to calculate the volume of a solid revolution. There's other methods such as the Washer method or the shell method, but in this video we're only going to be taking a look at the disk method. So consider a function f of x with the bounds a and b. Also consider the area underneath this function. What if we were to rotate this function around a specific axis? For example, let's say the x-axis. What would that look like? So this specific function would basically form like a air horn type shape around the x-axis, and that's basically what a solid revolution is. It takes a function and it rotates it around a specific axis, creating some sort of a solid. Now let's say if we want to calculate the volume of this solid revolution, how do we do that? Before going into the volume, consider a circle. And this circle would basically have a radius r. And if we want to calculate the area of this circle, we can basically use the formula pi r square, right? So just keep this in mind. Now let's go back to our solid revolution. And let's say if we want to calculate the volume of this solid revolution using the disk method, we're going to take a circle and we're going to insert it in our solid revolution. I'm just going to call it a solid. We're going to insert it in our solid, right? And the width of this circle is going to be dx, meaning it's going to be a very, very infinitely small number of x. And what we're basically doing here is we're going to take a lots and lots and an infinite amount of circles, and we're going to calculate the area of each of these circles, and we're going to add them up. And that's how we get the volume of a solar revolution. So to calculate the area of a circle, we need a radius. And how do we get that? Now, if you look at the circle over here, we can see that the middle point lies right at the axis. So we can basically say that the radius of any of the circle lying on the solid is gonna be the function f of x at that point. Because like, look at this. This point is gonna be obviously f of x, right? And what the radius is gonna be. From here to here, that's what the radius is gonna be. This entire thing is gonna be f of x. So we can say that radius is equals to f of x. So if we were to take many circles like this, obviously in this picture there's only a finite amount of circles, but when we're integrating, we're taking like when finding the volume, we're taking like infinite amount of circles, right? So if we find the area of each of these circles and add them up, that's how we get the volume. So what we're basically doing is we're gonna be, let's say this is A, this is B. I don't know why the A looks like that, but okay. So we're gonna basically say that we're gonna integrate the area of the circle from A to B, which is gonna be pi r square. And what is our r? So r. Our radius is gonna be function itself. So if we plug that in, our integral will be b to a and pi pi fx square. That's how we derive the formula for the disk method if you want to calculate the volume of a solid revolution. So let's quickly take a look at an example. Find the volume of x square when revolved around the x-axis from x equals to 2 to x equals to 4. So we are given a limit over here, so which is good. Uh, so we know the x square is basically a parabola. Let me draw one. It's a very lopsided parabola. So let's just say this is x is equals to 2, and let's say, oh my God, what am I doing? Let's just say this is is equals to 4. So if you only take consider this side, because this is the only side we're going to be working with, we can just draw it like this, right? That's going to be our function. And if we were to rotate this around the x-axis, it would basically look like this. And if you want to calculate the volume of this shape, we can just take many infinite circles, do not mind my circles, and we can just add them up. In other words, we're just gonna integrate the function. We're gonna integrate, what am I doing? Okay, from 2 to 4. The upper limit's gonna be 4, the lower limit's gonna be 2, and it's gonna be pi fx square from the formula we just derived. So let me just write it over here. That's something over here. We know that fx is equals to x square. So this will be, we can just write the pi outside of the integral because it's a constant. And this is going to be 4 to uh, x square square dx. If we were to evaluate this integral, it would be, uh, let me, so it's going to be pi square. So if we were to evaluate this, and pi x over 5, and the limits were 4 and 2, so we can just write 4 and 2 over here. And if we were to evaluate these limits, then we would get 198.4 pi. That's gonna be our volume for that specific solar revolution. So that's how you calculate the volume of a solar revolution. Let's say if we were given a function f of y, right? Or let's just say we were given any function and we have to rotate it around the y-axis now. If the function was given in terms of x-axis, we would basically turn it into a function in terms of y-axis. But if it's given in terms of y-axis, then we can just work with that. And yeah, the idea is gonna remain the same. We're just gonna rotate it around the y-axis. And but in this case, the radius will be f of y instead of f of x. So keep that in mind. If it's rotating around the y-axis, the radius is going to be f of y, and if it's rotating around the x-axis, the radius is going to be f of x. And yeah, so we can just evaluate it from there. So yeah, that was it. That was a really quick brief of how we use the disk method to calculate the volume of a solar revolution. Yeah, thanks for watching.